Module 2. Testing, Performance, Durability, and Practical Applications of Civil Engineering Materials. 1. Introduction to Material Testing. In civil engineering, you don't just pick a material because it looks strong or feels sturdy. Every major material used in construction undergoes rigorous testing before approval. These tests tell us how strong it really is, how it will behave over time, how it reacts to temperature, moisture, or chemical exposure. Why this matters. Imagine constructing a highway bridge in a humid coastal city without testing the steel for corrosion resistance. Within just a few years, rust could compromise structural safety, and the cost of repairs would be huge. 2. Mechanical testing of materials. A. Tensile testing. Measures a material's resistance to being pulled apart. Produces a stress-strain curve showing yield point, ultimate strength, and elongation. Example. Before using steel reinforcement bars, rebars, in high-rise buildings, they are tested to confirm they can handle design loads without snapping. B. Compressive strength testing. Crucial for materials like concrete, stone, and masonry. Involves crushing a specimen until failure. Example. Concrete cylinders are often tested at 28 days after casting to ensure they meet design specifications. C. Flexural testing. Measures bending strength. Important for beams, slabs, and pavement materials. D. Impact testing. Determines a material's toughness, ability to absorb energy before breaking. Common for bridge components exposed to accidental collisions. 3. Non-destructive testing, NDT. Sometimes you need to test a structure without damaging it. Common NDT methods include ultrasonic testing, sends sound waves through materials to detect cracks. Rebound hammer, estimates concrete strength by measuring surface hardness. Radiographic testing, uses X-rays or gamma rays to detect internal flaws. Example. When inspecting an old dam, engineers might use ultrasonic testing to ensure that internal cracks aren't forming inside the concrete body. 4. Durability and deterioration mechanisms. Even the strongest materials degrade over time. The main culprits are A. Corrosion. Especially in steel, caused by moisture and oxygen. Salt water accelerates corrosion, making coastal structures more vulnerable. Example. The Westgate Bridge in Australia required extensive steel rehabilitation due to corrosion from sea spray. B. Freeze-thaw damage. Water enters pores of materials like concrete or stone, freezes, and expands, causing cracking. C. Sulfate attack. Certain soils and groundwater contain sulfates that chemically react with concrete, causing expansion and disintegration. D. Alkali-silica reaction, ASR. Chemical reaction between cement and reactive aggregates. Produces a gel that swells, leading to cracking. E. Biological attack. Timber can be attacked by termites, fungi, and marine borers. Concrete sewer pipes can suffer from bacterial acid corrosion. 5. Protective measures. To extend material lifespan, engineers employ strategies such as coatings and sealants, paint, epoxy, or galvanizing for metals. Cathodic protection, using sacrificial anodes to prevent steel corrosion. Waterproofing, membranes or admixtures in concrete. Timber preservatives, chemical treatments against termites and rot. Example. The Channel Tunnel between the UK and France uses cathodic protection to safeguard the steel reinforcements in its concrete segments. 6. Environmental impact and life cycle assessment. Modern projects must evaluate embodied energy, total energy from material extraction to disposal. Carbon footprint, greenhouse gases released. Recyclability, ability to reclaim materials at the end of a structure's life. Example. Many new office towers in London use recycled steel beams from dismantled buildings, drastically reducing carbon emissions. 7. Case studies, materials in action. Case study 1, Sydney Opera House. The shell roof is made from precast concrete segments. Unique ceramic tiles chosen for both aesthetics and resistance to weathering. Case study 2, Millau Viaduct, France. Uses high-strength steel for its slender piers. Steel was chosen over concrete for reduced weight and faster construction. Case Study 3, Hoover Dam. Used a special concrete mix with low heat of hydration to prevent cracking. Aggregate was carefully sourced to avoid alkali-silica reaction. Case Study 4, Akoshi Kaikyo Bridge, Japan. Located in a seismic and typhoon-prone region. Uses weathering steel with special protective coatings to resist salt-laden winds. 8. Modern innovations in civil engineering materials. A. Self-healing concrete. Contains bacteria or microcapsules that release healing agents when cracks form. B. Ultra-high performance concrete, UHPC. Extremely strong and durable, allows for slender, elegant designs. C. Recycled plastic composites. Used in decking, benches, and even pedestrian bridges. D. Smart materials. Materials with embedded sensors to monitor stress, temperature, and corrosion. Example. A bridge in Italy uses smart concrete with embedded fiber optics to send real-time structural health data to engineers. 9. Material selection for specific projects. The process involves identifying performance requirements, strength, durability, fire resistance. Considering environmental exposure, humidity, temperature cycles, chemical attack. Evaluating cost and availability. Assessing sustainability goals. Example. For a desert solar power plant, engineers may select concrete with special admixtures to handle extreme heat cycles and minimal water availability for curing. 10. Future trends. Looking ahead, civil engineering materials will continue to evolve. Expect more bio-based materials like hempcrete. Greater integration of recycling into supply chains. Wider adoption of modular construction, which requires precision-engineered components. Materials engineered at the nanoscale for enhanced strength and durability. 11. Summary of Module 2. In this module, we have examined material testing methods, both destructive and non-destructive. Explored durability threats like corrosion, chemical attack, and biological damage. Discussed protective measures and sustainability considerations. Looked at real-world case studies that link theory to application. Considered modern innovations and future trends in material science. The key takeaway, choosing the right material is not just about strength, it's about the whole life cycle, environmental impact, maintenance, and adaptability to future needs.